Now that we've shown P implies Q or R goes to P implies Q or P implies R, we're going to move ahead to the next three examples in classical logic. Next episode will be the last three. So we have a few, I already declared a few of the classical built-in theorems that I thought might be useful for each one of these. So for the first one, I thought probably that byContradiction will be useful, but I don't know. We're gonna see if that's the case or not. I went back and renamed some of these theorems, some of the examples to theorems, so that they correspond to what's in the classical library. And also so that we don't accidentally use them, we wouldn't want to use exactly what we're showing. There's not much of a point in that. In other words, we could solve this with exact classical dot not. We're proving this one direction, so this would be dot MP. But we're going to do it the hard way. After we introduce our not P and Q, what can we really do here? We're kind of stuck, right? Because we can't get the P and Q out of the not P and Q. We can't really do much with a proof by contradiction either, because if we try to, we get stuck again with this expression, right? Hn here being not P or not Q doesn't seem tractable. After getting stuck on this one, I'm going to try to split it into two different implications, because I know that this is actually an if and only if statement, because that's proven in classical. I want to split it into two cases, and I'm going to show each one, because for me, it's a lot more intuitive to prove the reverse case, where or not implies not and. All we have to do is we have to pattern match on either case of the or. So HNP or HNQ. And depending on which one we're in, we can show that there's a function from P and Q to false. And in the second case, we can show the same thing. Okay, well, how can we do that? Well, we can say that if we have an HPQ, which is P and Q, and we need to show false with a function from not Q, we can just apply HNQ to HPQ dot right, and HNQ to HPQ dot left, HNP to HPQ dot left. So for me, this was very intuitive. The first one, though, is a lot harder for me to do. And it's because we can't just case split on the intro, on the hypothesis. Everything in this is a function, and that makes things harder. Plus, we can't show the goal, which is an or. We can't show it with just either side, right? We don't have enough information to show just not P. We have to show both not P or not Q at the same time. After thinking a little bit more about this and also the, no pun intended, also the second proof that we did, I finally realized that or not imp not and is possible to show because of the pattern matching, right? Or in the goal is not trivial. There's no way you're going to be able to prove this by first showing not P and then showing, or dot injection right with not Q. You have to show both of those at the same time, which means that we have to create an or. We have to pattern match on something first. We have to create an or first. So to do that, we're going to use classical EM. And once we've figured out that we need to use classical EM here and not, a proof by contradiction or something, we basically solved this proof. That's the only hard part. The hard part is just recognizing that if you have an or in the goal, you need to use classical EM if you don't have another way of showing it. Before we got to classical, we had lambdas to just spontaneously introduce arguments, but those won't help us here much. So instead, we have another way now that we're using classical of introducing arguments, and that's classical.em. So we're going to obtain either P or not P from classical.em P. And now that we've done that, right, the same idea, of pattern matching on either side applies, and we can pattern match with, let's see here, these are just going to be sorries. Here we can show either case by now using the or dot injection right or injection left, depending on what we are assuming from the EM. So if we have P in the first case, and we have to show not P or not Q, we have a function from P and Q to false, and we have P. And instead of trying to handle each case at once, what we're going to do is we're going to say we have P or not P. We're going to use this lemma, HEM. We're going to rewrite on either side to get the expression that we need. So we're going to rewrite P into not P and or not Q, and we're going to rewrite not P by HM, function expected. It's an if and only if, so we have to use rewrite. Okay, now we have not P or P, so we're already really close here. So now we just have to show that we can get to, from P, we can get to not Q. HP and Q, which is of type P, implies not Q by lambda HP goes to. And now we can do a proof by contradiction. And now the opposite of what we're going to show is not Q. And from that, we'll be able to show not. Let's just get HQ from HN and Q. So now we have P and Q. So now obviously we can show false because we can just say P and Q or something, whatever the ones with and NPQ, do HP, HQ. Okay. That's a bit involved. I'm pretty sure that there's a better way to do that because we're using EM and byContradiction at the same time. It's probably possible that you only need one, maybe just contradiction or something, but it's a bit tricky. These are definitely step up in difficulty from the non-classical proofs. In this one, the key was recognizing that to get to an OR as a goal, you had to use EM to build that OR and then pattern match on either side. You could pattern match on either side. Both of these, I mean, you don't have to use rewrite here. I'm sure that there's a way to do this without rewriting, even, I mean, just by pattern matching. To me, this made more sense because I wanted to preserve once we had the OR, so once we had P or not P, I wanted to preserve that and show, you know, exactly the goal, which I forgot to show actually. We have to say exact CM at the end because now we have, we have to say, we haven't finished. HP and Q maps the P to not Q. So we have to say or dots imp, I believe it's going to be imp right. And this is going to take a function. It's going to be our imp right HP and Q. There we go. Awesome. So this is just taking our OR and mapping the right side from P to not Q to end up with our goal. Awesome. Okay, so when we were at this stage, the key was recognizing that we needed a function from P to not Q, and that given a P, we could show not Q by assuming not Q and showing a contradiction. When we have P and not Q, we can build a P and Q, and we have not PQ, so we can show false from that. Okay, wow. Hopefully the next ones will be easier to do. All right, so next we need to show that negation of an implication implies P and not Q. And I added the second way again. To get ourselves a little bit prepared, we'll show the first way. We have HP, H not Q, sorry. We need to show not P to Q. Well, that's just a function of a function, right? So say exact, and then we have lambda HPQ goes to what? So now we have HPQ, we have H not Q, we have P. Okay, well, clearly we can apply HPQ to P to get Q. And we can apply H not Q to Q to get false. And we're done. That shouldn't be too hard for you. If it is, you should go back and watch the videos about pre-classical logic, okay? But this needs classical logic. And I'm just assuming that because it's in this classical section, right? So let's see why. Well, it needs classical logic because if we're given, let's just do intro H and not Q. If we're given an H hypothesis of not function, then we need to make a function. That means we need to make either a function from P to Q or prove P and not Q somehow using this not function, right? Without classical logic, it seems kind of clear to me why you wouldn't be able to do this because it's just so intractable, right? What are you going to use? If you're here, you have this and the goal of P and not Q. How on earth are you going to get a P? How on earth are you going to get a not Q from this? So let's try using, what do we want to try using here? Proof by contradiction. In the first example, we showed that not P and Q gives us a not or. So maybe we can start with that, right? We can start with a proof by contradiction. Let's just see where this takes us, right? We will show, let's see, proof by contradiction, exact by contradiction, and HN is going to be HNP not Q. This is going to go to false, right? So we're going to show that given this, we can prove false. We have a not and, which means we can apply our theorem, not and imp or not at HN and Q. We're going to rewrite our theorem that we already proved at HN, P, and Q because it's a not and. So we should be able to write it into an or. I don't know if that'll help us, but let's just see. So we're getting an error. We're saying quality or proof expect. So this means that we didn't actually use an if, which is classical's not and if or not. So let's just prove that real quick. And of course we can prove that by, let's copy and paste these. Now I know we could use apply instead of going through all this rigmarole, but we're going to probably want to prove this anyways. We just need to build this from not imp. These names are long. I'm not going to try to find them. That and that. That's quite a lot. Okay. All right. So we've proven not if and or not. Not and if or not. Now we can rewrite it. So now we get P or not Q. We can, of course, rewrite the not as well. We don't actually have not here. How do we have classical? Not. Okay. And then that's going to take care of that not Q. And so we're doing two steps at once here. So now we have not P or Q, and we have to show false from that. But now we have something that we know how to handle, right? We have a hypothesis that's an or. That means we're going to do HN, P, Q with, let's just do, we don't need to name these. Oh, no, we do need to, and this is Q. Okay. All right. So we need to show false from not P, and not P implies Q. Maybe we don't want an or, right? Because we're trying to prove an and. So let's try not using our previous theorem. Let's go all the way back up to here where we had H not P implies Q. So to show this one, we need to use something from classical. We know that. But why do we want to use classical.em? And why do we want to use P specifically for that? So I already tried this proof. I was stuck on it for a while. I already tried it classical.em with Q, and it becomes pretty hard in the second case. In the first case, it's not so bad to show because you can make a function from anything to Q of type P if you want, and then you can give that to HNPQ and solve the first case. But in the second case, you have a function from Q to false, not Q, right? And it's pretty hard to show, at least it was for me, it was pretty hard to show P and not Q just from that. So I wanted to talk a bit more generally because, obviously once you know which, specifically which function from classical to use, these proofs are not so hard, right? But it's getting that function, getting that, that key to the proof that's the hardest part. The trick here is to recognize that when you do, obviously we don't have an or in the goal, so it's not so obvious as the first time where when we had an or in the goal, let's see, in the first part of the video, not P or not Q, well, clearly we can do, classical.em P and then map whatever, P to not Q somehow, right? It's not so clear why that this would help us, this same approach would help us to show P and not Q, because we're splitting the goal into two parts, right? And the reason is because the implication in the hypothesis, the P implies Q in the hypothesis, there's a relationship in logic between an implication and an or. An implication says that from P I can show Q, but it's implied, no pun intended, that if you can show Q from P, then you must not have, if you have P, then you must not have not Q, right? Well, or something along those lines, right? So there's some relationship between P to false, in other words, not P. You don't have P, well then you don't have Q because you can't use your function, right? You can't use the implication. So in other words, that was a lot of words to describe what exactly is going on here, which is that we have from classical.em, we have a function from P to false. This is our not P. And in our in our hypothesis, HNPQ, this is a not of P implies Q. And the relationship that I'm talking about between an or and an implication is that this, what you get on the right side of the or, is rewritable as P implies Q, right? Because ex falso quod liabet says false implies anything. So we can, say after P implies false, we can make a function from P to Q by using this function. So we're going to use that in our proof. This is going to be a proof by cases. And in the first case, we're going to have P and Q. This is where we're going to use suffices. Suffices lets us simplify the goal, right? Because we have already shown P, and if our goal is P and not Q, then we should be able to tell Lean that we just want to show not Q, and that's what suffices. So H not Q of type not Q to give our new goal a name. And this naming is important because we have to name it in our expression, right? We have to show that from something we can simplify the goal, and that something is just going to be what would have been the last step of our goal, which is and.intro HP HNQ. So this is the one where we have HP available to us, the first case. So we can say, oops, run instead of the walrus operator. Okay. So now after that, the goal becomes not Q. So to show not Q, a function, we use a lambda. Always use a lambda to show a function, to show implication. And this is going to take an HQ, because it's going to take a Q, and we need to show false from that, right? Well, we have HNPQ, which is a function to false. We just need to give it a function from P to Q. But we don't even need to use the HP here. I'm going to use an underscore. And we're just going to directly give back, this is going to be a constant function of HQ. And that closes the goal, because we've given HNPQ the ingredient it needs to prove false, which was just a lambda to HQ. And we had that by assuming HQ as our lambda, right? So this is a function HQ. This is a function from Q to false by composing HNPQ with HQ with a constant function, not composing, applying. Okay, so what about the second case? The second case is harder. We need to show P and not Q from not P implies Q and not P, right? We have a function from P to false. Well, this is what I was talking about, right? This is where we're going to use that. We have a function from P to false, which can be rewritten as a function from P to Q. It's equivalent. It can be, what's the word to use there? Specialized, maybe, because false implies anything. So we should be able to have a function from P to Q. We're going to call it HPQ. That's P implies Q. And we're going to have that by, let's just get this out of the way real quick. We have HPQ by sorry, and we're going to say, let's just make sure we can prove the goal. HNPQ exact HNPQ of HPQ. That should prove the goal. It doesn't, because we actually need to show something specific, not just false. So we'll just add an elim to that. False.elim. Okay, perfect. Now we just need to show P implies Q. So to show P implies Q, this is a lambda, so we get to assume P. And now it's funny because we are kind of doing a variant of what we had up here where we get to assume HP. But we have to show Q. We don't get to assume Q this time. Instead, we get to use the fact that we have assumed HP, but we also have HNP, right? So we can get false from that. And then we can just do a lim on that false to get whatever we want, right? Because remember, this was the case where we had HNP up here in the obtain. We did classical.em. Okay, wow, great. So that seemed easier, but that's because I, edited out all of the parts where I was bashing my head against the table. These proofs can be really tricky, and some of these take me a long time. Finding the classical.em is tricky. You got to try different. Sometimes if you don't recognize these properties, like the relationship between P implies Q and not P, you have to find these properties the hard way. Try different values of classical.em. Don't be afraid to try things, see what you can get, because it is, many times it's a journey, it's a process. So good luck.